All right, now we will look into a new topic on the fault tolerance, which is failure detection. So we need to address issue that we can how can we reliably detect that a process has actually crashed. So there is a general model for it where each process is equipped with a failure detection module. So when a process P probes another process Q for a reaction, so basically if Q reacts, so the process Q is considered to be alive by process P. But if Q does not react within a certain amount of time, so basically Q is suspected to have crashed. So when we have this assumption, so in a synchronous system, a system is suspected to crash, and it is called when a system is a suspected crashed. So basically, it is a known crash. So the practical failure detection. So if P did not receive any heartbeat or any acknowledgement or any replies from the communication from Q within time T, so basically P will suspect Q. And if Q, the process Q, later sends message which is received by P, so the suspicion or this P will stop its suspecting Q, and P will increase the time of value T. So if Q did crash, P will keep the suspecting Q. So basically, the process P, when they want to assume that process Q crashes or not, so it relies on whether they receive any acknowledgement or any replies or any message from process Q. Otherwise, they will keep suspecting that Q has crashed. So in the by using that general model, so what can go wrong? First, there are several things that can go wrong, which is the first one is the client is unable to locate the server, and the request message from the client to the server is lost, or the server crashes after receiving a request, or the reply message from the server to the client is lost, and also the client crashes after sending a request. This is some situation where uh, using the general model might have problems. So basically, the two easy solutions, which is this is what usually commonly happen. So, for example, the problem of cannot locate the server. So basically, we uh, basically to have this kind of error, we can raise an exception where we can solve it by just report back to the client, and by the programmer may write special procedures in the program that invoke using specific errors, so that the in the next message where the request was lost, so we can just resend the message. So the OS or client start can start a timer where they when they sending a request, if the timer expires before a reply or acknowledgement comes back, so the message is sent again. So this is one easy fix for the situation. Next, in a super reliable group communication, just now we talk about sending message. So we need a distributed system need an intuition. So what it means by is distributed system need an intuition. So we already learned about the process group. So the intuition is a message will be sent to a process group G, should be delivered to each member of G, which is being the process group. So this is important to make distinction between receiving and also delivering message. So in a situation where a sender send message to several recipient in the process group or in where the respects the process group members. So a message is said to be received by a message handling component. Oh, I forgot to change the pointer option. So a message is said to be received by a message handling component, and while in turn the message handling component will deliver message to the component containing the core functionality of the group members. So basically, this is the differences between receive and delivery. So receive, the message handling component receive a message from the sender, and deliveries mean message handling components send message to the group membership functionalities. So in a less simple reliable group communication, basically, a reliable group communication in the presence of faulty process, the group communication is said to be reliable where it can be guaranteed that the message is received and subsequently delivered by all non-faulty group members. So the tricky part here is that we need an agreement, okay, on what the group actually looks like before a received message can be delivered. So for example, suppose we have process A, and process A sends a message to the process group. While message traveling the network, process B crashes. So some members might receive the message and deliver it to the application, uh, and thinking process B is the part of the group. So but others process might have detected that process B crashes and decided that the message shouldn't count because the group has changed. So this lead to a divergence in the state between the process group members, because different members has different version of what is actually happened. So basically that's why we in the reliable group communication, in agreement is needed. Okay, so in a simple reliable group communication, this is the solution. So in a reliable communication, but if we assume non-faulty process, so reliable communication now boils down to reliable multicasting, where a message is received and delivered to each recipient as intended by the sender. So in this diagram, there are actually two parts here. This one is part A and this one is part B. Both are solution for reliable multicasting, but for part A, it is for message transmission, and for part B is reporting feedback. So what happened here is sender assigns sequence number to each multicast message. So when they assign, they numbered the multicast message, and they will store the message locally in this history buffer. So the receiver will return the acknowledgement. This one kat bawah ni, at the bottom, right? Receiver will return the acknowledgement. So a receiver can suspect there is a missing message when it receives a message number higher than the current message. So for example, here the message number is M25. So the last received message of this receiver is 23. So basically here the receiver, when the last received message is number is 23, and the current received message is 25, which is higher than uh, the supposed received message. So basically, the receiver return negative acknowledgement to the sender, saying that they missed message number 24 and asking for retransmission of the message. So now let's talk about commit protocol. So there are two protocol scheme, which the first one is the one the let's talk about the distributed commit protocol. So the problem here is we have an operation that being performed by each member of a process group or none at all. So under reliable multicasting, a message is expected to be delivered to all recipients. While in the distributed transaction, each local transaction must succeed. So there are two protocol scheme that address this, which the first one is the one phase commit protocol, which is not here. So the one phase commit protocol is when the coordinator tells all workers here. I mean, if we look into the hierarchical structure of process group, so we have the coordinator and also the workers, right? So in this case, workers is also called as participant. So in the one phase protocol, the coordinator will tell all workers to uh, locally perform the operation, okay, that needs to be done. Also, the disadvantage is if one worker cannot do it, so they cannot tell the coordinators. So the local commit violate the concurrency the concurrency rules. So this and then we have another one which is two-phase commit protocol or 2PC, but the one-phase commit protocol is this part. So because uh, there is a problem with it, so basically there is an improvement on the uh, for the second phase. Sorry, two phase. So for the two-phase commit protocol, it most commonly used by distributed system, but there's a drawback where cannot we cannot make the coordinator fails. If coordinator fails, a huge problem will happen. And in distributed commit, usually performed by the coordinator. So what happened here is the essence in the phase one, we're talking about the two phase. The client who initiated the computation will act as the coordinator, and processes will require to commit are the participants or the workers. So under phase 1A, so the coordinator sends a vote request to participants, which is also called as pre-write, and under phase B, when the participant receive vote request, it returns either vote commit or vote abort to coordinator, meaning they will vote yes or no. So if they saying yes, vote for yes to do the to do the computation. So basically they will send vote commit. But if they said no, so basically they will send vote abort to the coordinator. So if the participant sends vote abort, so it will abort its local computation. So no, they will not do any work. So under phase 2A, coordinator collects all votes. If all vote commit, so meaning here there is a collective vote among all of the participants. So if all of the participants say vote commit, so it sends global commit to all participants. Otherwise, it sends a global abort. So it needs to be collective decision. And each participant waits for global commit or global abort and handles it accordingly. So in essence, the coordinator and also the participant are in three main state, which is init, abort, and commit. Same with the participant, but the differences under wait and ready state between the coordinator and also participant. So this figure shows the state machine for coordinator participant. So basically, let us look at the coordinator first. So under the coordinator state machine, so we have this one, which is the init state, meaning they start the transaction, so they send a vote request to all of the participants. So basically, what happened here is when the state move to wait state, the coordinator will send vote request to everyone and waiting for them. Everyone means all of the participants and waiting for them to vote. So if all vote yes, which is vote commit, so it moves to commit and tell the group. So tell the group meaning the coordinator will send global commit to everybody. But if any of the participants say no or vote about, so basically there are two things that will happen. So it moves, the transaction will be cancelled, and they will they will discard of the local operation. So basically, for the participants, same they will start with init, meaning waiting for prepare message uh, from the coordinator. So now under ready, which is the most important state for participant. So participant finish uh, the participant will start locking the database, and if they vote yes to coordinator, so they are already legally bound to the legally they are bounded to the decision. And then if yes, it will move to global commit. But if they vote for vote abort, so they move to the state based on the coordinator message for global abort. So if we want to analyze, should we have a should there is any failing participant, so what will happen? So in this case, what happen when a participant crashes? So after recovery, uh, when the participant crashes, so and they recovers, what should the participant do to stay consistent with the global transaction? So here are the recovery on each state. Meaning here it says participant crashes in state S and recovers to S. Meaning when the participant, any of the participant crashes in in state S means any of this state, right? What should the participant do to stay consistent with the global transaction on that state? So the recovery will very much depend on which state the participant was in when it crashed. So if when the participant are crashing in init state, so when they recover under init state as well, so basically no problem, because at that particular point participant has not yet voted. So if participant crashes in this state, nothing will happen. But if the participant crashes under ready, okay, this is quite important. So when the participant crash under ready, it means that participant has already voted yes or no. So but the thing is, when they recovers, they actually may have a situation where they might not know what they have voted for, or what is the global state of other participants in terms of voting. So participant who is waiting to either commit or abort after recovery, participant needs to know which state transition it should make. So what they can do is they just look at the log of waiting for the coordinator's decision. So before crashes, they might have logged something. So participant must check its log and see it was in ready. Contact the coordinator, and then ask the coordinator whether the transaction is committed or aborted. And then we have a situation where participant crashes in abort state. So to recover, so basically they merely make entry into abort state independent. So if participant crashes here, they just need to simply redo the abort. So independent here means that they need to doing it multiple, even if they are doing it multiple times, it still has the same effect. Okay, even if they have done it before, they crash, if the participant has crashed and they have done something, so even though they redoing it things that they have done before they crash, so it still have the same effect. So what are those things that they might have done? So basically, they remove temporary file, they release a log, and also they clear their workspace. If they under the commit, so under commit, if the crashes, and when the participant crashes uh, in commit state, so they will also be entered into commit state in the bottom. So redoing commit is safe. Participant do all transaction in time space. So only move result to permanent storage after commit. So there is an alternative where when recovery needed is needed to ready state, so they will check state they will check state of other participant, because previously I've already said that under when any part of the participant crashes in ready state, so they when they recover, so they need to wait for the coordinator's decision. They need to lock the coordinator's decision. So basically they don't need to do that. There's another alternative where when a recovery is needed to ready state, so the participant need to check state of other participants. So meaning the process need to check the state of other process. So no need to lock coordinator's decision, because there might be a situation where the coordinators failed. So basically recovery participant, for example, if we have two process, P and also Q. So P is the process that is crashes and suddenly recovers in that particular state. So they will contact another participant Q to see what is the state of Q, because we need to you have to understand that the state of the all of the participants in the process group might be the same, because they are making a collective decision. So basically, if the state of Q is commit, so action by P is they make transition to commit. If it's abort, so this one is easy. Commit abort init is easy. Okay, they just continue, because even if they are doing things, the same thing all over again, so basically it won't have any effect on the transaction. But when they are in ready state and they contact another participant, so P decides based on the state of Q. So if Q never voted for yes meaning vote commit, so the global commit is impossible, because we already know that in a distributed system, if one of the participants say no, so basically uh, the coordinator will call for nothing will happen. So if all participants are in ready state, so the protocol will block. So basically, by saying block, apparently we already knew that coordinator is failing, because they cannot move, because the coordinator is the one who decide based on the collective vote that the global state will move to commit or abort. So when all of the participants are in the ready state, so they already knew that the protocol blocks because the coordinator is failing. So note that the protocol prescribed that we need a decision from the coordinator. Uh, I'm not sure why we cannot move to the next slide. Okay, let me change the laser pointer. Okay. So now let us talk about the failing coordinators. So the real problem lies in the fact that the coordinators final decision may not available for some time, meaning they crashes and they have not recovers. So basically here the problem is the participant doesn't know if the coordinator has made a decision whether to commit or to abort. So this blocking can be uh, indefinitely. Um so the system can be looked as the whole system can be looked as halting or crashes. So if the coordinator by saying the whole system meaning the whole distributed system, because we know that the distributed system consists of a group of process. So the whole process seems to look as stopped, yeah, because they have been blocked by the 2PC protocol. So if the coordinator never recovers, so participant may stack locked will continue to be locked until there is a human intervention, meaning intervention mean they restart or anything lah. So in previous slides, participant that in ready state must wait forever. So let a participant P in the ready state time out when it has received the quality decision. So P tries to find out what other participant knows, which is has like has been discussed earlier on. So the timeout based alternative allow already participant to query others, but if all participant and the connector has failed, no participant has sufficient information to decide, causing the protocol to continue to block. So this problem is actually a very fundamental problem. It's not because of due to implementation flow. So we need to understand 2PC is a blocking protocol where participant cannot decide without coordinator. Hence the reason why we have another protocol which is 3PC, but it's not part of the solution that I will discuss here. So when the system fails, when failure occurs, so basically we need a recovery process. So recovery means that we create an error-free state. So so we have two type of recovery, which is forward error recovery and also backward error recovery. So forward error recovery is we find a new state from which the system can continue the operation. So then we have another type of recovery. So then we have another type of recovery, which is backward error recovery. So what happened here is in backward error recovery is we bring the system back into previous error free state. So what happened here is the system will record their state from time to time. So if there's an error, so basically the system will roll back to the last safe version of the system. So this is the most common recovery method in distributed system, in any distributed system. So when we use backward error recovery, so it's requiring us to establish recovery point. So recovery point is the usually is the last safe state. So meaning we need to at time from time to time we need to save the system, like for example like Microsoft Word or Microsoft Excel. So if you do not press the button save, the system is with the system, the software itself has a mechanism in self-saved from time to time. So when there is any problem with your system, if your OS crash or the system, the Microsoft Word freeze, for example, halting. So basically, you already have the recovery of the software based on the last saved version of the uh, Microsoft Word or Microsoft Excel. So when you open back your laptop, open back your OS, so you can see that they will um, point you to the last save last state point in the Microsoft Word. So that is what we call as recovery point. So the recovery in distributed system is complicated by the fact that process need to cooperate in identifying a consistent state from where to recover. Okay, in the distributed system, if when I talk about the Microsoft Word or Microsoft Excel, so basically we are talking about a single software, right? By that is used by a single user. So basically, the recovery process is easier. But in a distributed system, when the Microsoft Word and Microsoft Excel is shared in Google Drive or in OneDrive, right? And the system itself is the software is used by multiple users, then the recovery is process is getting tricky. So here, for example, this is the requirement of the consistent recovery state. So we have the consistent recovery state and inconsistent recovery state. So to say that a recovery state is consistent, so every message that has been received is also shown to have been sent in the state of the sender. So we here assuming processes regularly checkpoint their state. So the most recent consistent is the global checkpoint. So see that in the figure, there are two checkpoints. So two checkpoints here. Okay. So this one, this one is the checkpoint. All right. So let's look at move away to the most recent checkpoint. So there are local checkpoints where the state saved by a process, and then we also have the global checkpoint. Global checkpoint is the checkpoint from each process that form a consistent snapshot. So we want to determine which one is the consistent snapshot. So a consistent checkpoint pair means if, for example, P2 says it had received message from P1, so there are two. Okay, so we look at these two checkpoints. Okay, so P2 says that it has received message from P1, so P1 must have sent that message before its checkpoint. So basically here, so if message is received after, okay, so if message is received after the recovery line is the dash line is said to be in an inconsistent state. So basically this is the checkpoint. So the uh, uh, here if you see that the P1 sent after message, okay, after the checkpoint. So this is the inconsistent. So this one is the consistent state. Okay, this one is consistent state. So then when we talk about the checkpoint, there are two type of checkpoint. First is coordinated checkpoint. Second is the independent checkpoint. So what is the difference between coordinated checkpoint and also independent checkpoint? So basically here, uh, going back to my example of Google document or your Microsoft Word in OneDrive, where it is edited by multiple users from locally. So basically, coordinated checkpoint means every users uh, saving saving the document at the same time. So that is coordinated checkpoint. But for the independent checkpoint, every local users are saving the document at different time. Okay, it looks like for the content checkpoint, it looks like when we talk about Google document, it looks like kind of like impossible. People want to save it at the same, but I just want to give the example, the analogy of what is the difference, okay, between the coordinated checkpoint and also the independent checkpoint. So in essence, for the coordinated checkpoint, each process takes a checkpoint after a globally coordinated action. So it is a very simple solution using two-phase blocking protocol. So a coordinator will multicast the checkpoint request message. So when the participant requests such message, it takes a checkpoint, stops sending application message, and reports back that it has taken checkpoint. So when all checkpoints have been confirmed and the coordinator, so the later broadcast a checkpoint done message to allow process to continue. So basically, the checkpointing is coordinated by the coordinator. Hence the reason why when I give example of saving the Microsoft Word at the all of the users of that edits the Microsoft Word, saving it at the same time, it kind of doesn't make sense. But we are talking about an automated uh, recovery, automated checkpointing. Okay, not like the one pressing the button save. No. Okay, so basically, but the idea here is the coordinator will make sure that every process do the checkpointing, which is saving their state, saving their current state uh, at the same time. So now we have another one, which is the independent checkpointing. So this is kind of tricky. It's kind of tricky because, like I said, the multiple users or multiple process can do their checkpointing at any point of time, because they are not really coordinated. So basically, here, each process will decide on its own when to take a checkpoint. So there is no coordination with other process. It's kind of simple to implement, but it will cause another problem. So basically, the key idea here is the process, because we have many process, right? We or participant, if we look back at our previous terminologies in the 2PC protocol. So each process will periodically saves their current state, uh, meaning they are doing the checkpointing lah. For periodically save their state tu, maksudnya they are doing the checkpointing. So they will send message to other process and records who influence whom through the message. Because kalau kita tengok tadi uh, in the example of recovery here, so they need to establish a consistent checkpoint. So if one process fails and rolls back, so the other process must be forced to rolls back too. Uh, so this is kind of tricky because the rolling back may goes way before, all the way to the beginning. So here, each process, so inilah maksudnya which the risk of cascaded rollback to the system startup. Maksudnya they roll back way from the beginning, not at the certain up to the certain checkpoint, because it's pretty hard for them to find the consistent checkpoint. Yeah. So here let's CPI CP C here means the checkpoint. Yeah. So CPIM denote the mth checkpoint of process PI taken by process 1, process I, and at the interval M, which is the time interval between the two checkpoints. The two checkpoints. So this is the checkpoint 1, and this one is the checkpoint 2. So when process PI sends a message in interval M, so it will piggyback. So basically, IM. Basically, when process I uh, send message during the interval, so it will attach extra info. So this will help the receiver to know where the message fits in time. So basically, this one is the last save, and this one is the next save. Yeah. So when process PJ, okay, the next process, the second process, receive the message in interval JN, it records the dependency of INT interval I and also interval M. So what PJ did in interval N depends on what PI, which is the first process tadi, or what PI did in interval N. So this dependency is safe, okay, when PJ takes PJ takes its next checkpoint. So why are dependencies is important here? So if we undo something in process PI, so the question is, do we need to also undo something in process PJ? So basically, if process PI rolls back to apa to uh, if process PI roll back, so PJ might also be rolled back. Meaning, tadi M minus 1 ni adalah the previous checkpoint. Previous checkpoint. So, here, the thing is, PJ use it, kenapa dia kena roll back kepada previous? Okay, because PJ, when they do the processing, they use information from PI. So, but now, for PI, so basically that information no longer exists after rollback. After rollback. Sebab PI tadi dah rollback. So when PI tadi dah rollback, so PJ pun mesti rollback because the operation of PJ is dependent on the information given by the PI. Okay, so this is where this one makes more sense lah. Maksudnya sekarang ni because apa, if checkpointing is done at the wrong instant, so the recovery line may lie at the system startup. So we don't really know P1 will roll back until how many checkpoints back, way back, right? So P2 must follow lah. Because you see here, P1 supplies information to P2. Okay. So that's all for this topic. We will continue our classes, our lesson in the next session. Thank you.